So now that we talked about the basic patterns of the periodic table, which include the periods and the rows, the periods, of course, will tell you the number of electron shells that any given atom will have, and then the families or columns will tell you the number of valence electrons on that very last shell. And then, therefore, you can figure out the valence of the electrons by looking at the periodic table, especially if you're talking about the columns which are part of the S or P blocks. You also know from the periodic table what are the last orbitals that these atoms are going to have. The first two columns will have S orbitals. Columns 13 through 18 will have P orbitals as the last orbital. And then in the middle, you're going to have, from between columns 3 to 12, you're going to have the D block, and then the lanthanide and actinide series will be F block elements. Now, we also talked on another video about the different families which you have in the periodic table, which are basically families of elements that kind of act the same and either have the same kind of metallic properties or the same kind of valence electrons in the last shell. But more useful is going to be dividing the periodic table into groups. So we'll talk about that at the end of this lecture series, but for now I just wanted to qualify a few more patterns about the periodic table. First of all, we talked about the fact that the periodic table is arranged in atomic numbers, or in other words, the atomic number will increase as you go towards the right and down to the periodic table. So the atomic numbers will be increasing going this way as well as going down the periodic table. So kind of like in this direction, right, as you go there in the periodic table. Now, that it will also relate to the size of the atom. Now, I want you to notice this particular thing. Now, remember, until very recently, we couldn't actually take pictures of atoms, and even then, we can only take pictures of slightly large atoms with the actual atom force microscope. So how do we determine the size of atoms? We actually don't really measure the size of atoms. We measure the sizes of molecules which are made out of these atoms. And then we figured out what atoms are going to be in those molecules, and we calculate the average size of the atom based on the constituent parts of the molecule. So think of it this way. When you measure H2O, for example, or a better example, when you measure salt, sodium chloride, okay, and you can actually measure the size of this molecule. So since you know it's made of sodium and chlorine, you can kind of guess the size of sodium and chlorine based on that information. And you measure the same thing of lots of different things that have chlorine, and you can actually kind of try to eventually guess the size of the chlorine. But that's the size of the chlorine ion. So this is what we call the atomic radii in terms of the ionic or covalent compounds clouds. And that's not really the real format of the atom. And that's why you see this strange pattern here where some of the noble gases seem to be larger, and they're going to be larger because they're going to be unreactive, and so they're not going to really be forming clouds. Okay. Now, also, we're going to talk about electronegativity in a second, and when we do that, you have to remember that as the atoms become more electronegative, they become a little smaller, and we'll talk about that, and it will all make sense. But notice that overall pattern of the periodic table is that as you go down the rows, they tend to overall to become larger. So the size of the periodic atoms are getting larger as you go down the rows. On average, there's a few exceptions to the periodic table, but on average, the atoms will get larger as they go downwards. Namely, the D block and F block elements, these and those, are major exceptions for those rules. But in general, the lower you go into the periods, the more the size is going to increase, because that means basically more shells, right? So it doesn't make sense. Now, and you go towards the right, that's where it gets tricky. In most cases, and again, with the exception of the D and the F blocks, which different patterns are going to manifest themselves in the DF blocks, and I'm not going to get into detail about why that happens. But excluding the D and F blocks and the noble gases, which are going to be large, because remember, you're measuring this based on atomic radii of compounds, in which don't really happen in noble gases. So this is sort of like best guess of their size based on their lack of reactivity. But excluding the noble gases, there's a pattern of getting smaller as you go towards the right in the periodic table. And the reason for that is that because as you go towards the right, you're going to get more protons. And as you increase the number of protons in the atom, you're going to increase the attraction force that the nucleus is exerting on the cloud, which is going to implode the cloud inwards towards the nucleus. So atoms towards the right size, or in other words, everybody in this row, for example, row 2, has the same number of layers, right? But since the atoms towards the right have more protons in the inside, the layer will be dragged inwards more. And that's kind of what explains the size pattern that you experience in the periodic table. Another interesting pattern that you see in the periodic table is the idea of electronegativity. Now, remember this size pattern here because it's going to be very important. Remember that the size pattern is going to be going down like this, and also are going to be increasing in this direction. Or in other words, the atoms are getting smaller towards the right, but bigger towards the bottom of the periodic table, kind of, right? So kind of like that is the pattern for size, with the exclusion of the center blocks. Now, when you study electronegativity, this is your pattern in the periodic table. Now, electronegativity is a term that refers to how hungry an atom is for electrons, how desperate the atom is to gain electrons. Now, the reason why people on this side of the periodic table are going to be very, very not hungry at all is because, remember, we talked about the fact that people on this side of the periodic table it's easier for them to give up electrons than to take electrons to complete their electron clouds. So they're more like givers than takers of electrons. And that's why they will have low electronegativities. Now, the atoms on the right side of the periodic table are more like takers than givers. And so they'll be more likely to take electrons than actually give them. And so that's why they're going to be so high in electronegativity. Now, why is it that you have a vertical pattern going on here as well? You see that the electronegativity is increasing as you go towards the right, but as you're also increasing as you go that way. So it's increasing like this, and that's why you get the overall pattern. Well, remember we talked about the size now. When the atom is smaller, you're going to have very, very tiny electrons. The fluorine atom, for example, which is right there, is such a small atom for its electron cell size that it's very easy for a new atom to be captured because the nucleus is very close to the outside of the atom. And so it's going to be easier for the fluorine atom to capture electrons. And I think of this as that the fluorine atom is desperate, freaking desperate, to actually become like neon. Because you see, who's going to be especially hungry for electrons? Someone who's already very large. And yes, sure, I could use one more to become just like a noble gas, but I have like 100 electrons, so I'm good. You know what I'm saying? But what about fluorine? Not only does he need one more electron to be just like neon, but in addition to that, he barely has electrons. So one more means a lot for him, which means hunger for electrons increases as you go towards the right side of the periodic table and towards the top, because these atoms are smaller and more hungry for electrons. Electrons mean more for them. Now, in this case here, why are the bottom especially likely to give up electrons? So think about it, it's the reverse of what you happen up there. People up here, sure, I'm willing to give up an electron so I become just like the noble gases. But I'm so small that, you know what? Electrons mean a lot to me right now. I don't have a lot of them, so I gotta think twice before I give them up. But the people at the bottom, yes, they are willing to give them up to become like a noble gas, and at the same time, they have so many, they won't even notice if one of them leaves. And you see how that's why people at the bottom are going to be more likely to give up electrons than people at the top, and therefore they're going to have lower electronegativities. I hope that makes sense, because it's going to be important on the next pattern that we talked about, which is metallic versus non-metallic elements. Now, this has everything to do with the electronegativity pattern that we just described. Okay? It's kind of like the opposite of being electronegative is to be a metal. A metal is someone who's a giver of electrons. So if electronegativity increases towards the top right corner of the periodic table, the metal character is going to increase on the opposite end of the entire table. So because it's metallic is actually the exact opposite of being electronegative, which means the atoms which will be more likely to give up electrons are going to be atoms which are big and might not even notice if one is missing, and that happen to be needing to give up an electron to become electrically stable, or like a noble gas on the outside, have a completed shell. And so people on the left side of the periodic table are especially desperate to give up electrons because they're almost at the point of being a noble gas. If, for example, sodium right here, he gives up one more, he becomes just like neon over there. Or potassium right here, he gives up one more, he becomes like argon over there. And so for people on the first column, they're especially desperate. So they're going to be the most metallic of them all. And then you have the second column, a little more metallic, and then the third column and so forth. Now, they're going to be even more metallic towards the bottom because they're so large that they won't even notice if an electron goes missing. Now, the exact opposite is going to happen on this corner of the periodic table where the electronegative elements are going to be at. These highly electronegative atoms are going to be so small and so hungry for electrons that there's no way they're going to be giving up electrons, and so they're going to be the least metallic of them all. So remember, metallic is the exact opposite of being electronegative, and that will make sense. Alright? So while on the left side of the periodic table you're going to have more metals, on the right side of the periodic table you're going to have the non-metals. And then in between here, you're going to have some which act kind of like metals, kind of non-metals. Now that we've talked about this, it makes sense for us to talk about the groups of the periodic table. Before we do that, let's talk about reactivity, which is putting both of them together. All right? So who are the most reactive elements in the periodic table? Well, it's going to be the ones which are desperate to give or desperate to take. So the most desperate to take are going to be this on the top right over there. I'm going to put this in blue so you can see it better. So the top right are going to be the most electronegative or the most reactive in terms of being takers. They are desperate to take electrons. They're going to be the electronegative atoms, right? Meanwhile, the bottom ones here are going to be the most metallic or the most givers of electrons. And so these corners of the periodic table are going to be the most reactive of all. The most likely to give and the most likely to receive. Okay? So the general pattern of the activity in the periodic table is that reactivity increases towards the corners of the periodic table, and on the left side it's going to be more reactive if you are more likely to give up, which means you're big, and on the right side you're going to be more reactive if you're more likely to take, which means you're small. And so that's why you're going to have the opposite, because when you look at the left side you're looking at metallic-like properties. When you look at the right side, you're looking at electronegative-like properties. And that's why it's upside down to each other on different sides of the periodic table. But in general, the corners will be more reactive than the middle will be. And that is the overall pattern of electronegativity of the periodic table. Now that we've talked about this, we can actually look at patterns of groups within a periodic table. And so there are several types of elements in the periodic table. And you see several of them listed here. And I'm not going to really talk about them in detail because, after all, this is not a chemistry class. But the most reactive elements in the periodic table will be the alkali metals, which are going to be very, very metallic. They're going to be very likely to give up these electrons and engage in chemical reactions in order to give them up. Second to them, you're going to have the alkaline earth metals, which are second in reactivity. All right? Then you're going to have the transition metals. Now, before you hit the transition metals, you hit this series here. Remember I taught you the soldier was going to put an opened up version of the periodic table? That is where you get what we call the lanthanide and the actinide series. Now, the lanthanide are sometimes referred as rare earth metals. And they're going to be found in several places around the earth, but they're very rare. And then you also have the actinide series, which were often referred to as the radioactive or unstable elements or metals. Then you have the transition metals, which include all of these. And the famous transition elements will include all those things like, cobalt and iron and gold and all those different kinds of elements. Then you have the elements which are going to be called post-transitional metals. Atoms which are kind of like weak metals or not very strong metals. We call those, they're not very metallic in nature. They are metals, they're still givers of electrons, but they're not really as givers as the other ones are. And in fact, there are some situations where they might even be takers. And that's why we call them weak metals or actual post-transition metals. Then you have the metalloids. Now, metalloids are atoms which are going to act sometimes like metals, sometimes like non-metals. And that includes things like boron, silicon, and so forth. Now, and you see some of them featured there as well. And then you're going to have the non-metals, which are going to be the ones which absolutely act like non-metals and most of the time are going to be taking electrons instead of receiving them. And then you have a special group of non-metals which is extremely reactive. It's the counterpart of the alkaline metals, and they're going to be desperate to take electrons, and they're going to be the halogens on this group of the periodic table right here. And then you have the noble gases at the very end, which are non-reactive at all. They're absolutely non-reactive. They will never react because they have full, complete electron clouds, and they're going to be gases, very weak interactions between particles. They do not like to react at all. Okay? And so you see here representations of these different groups of the periodic table and different elements which compose them, and I hope that this all makes a lot of sense to you, and you can understand that the patterns of the periodic table are going to be determining the kinds of elements that you get. Alright? So, in the next video, we're going to finish up the patterns of the periodic table. I'll see you guys then.